For decades, advanced chip manufacturing has been dominated by two giants. TSMC produces around 90% of the world's most sophisticated chips. ASML is the sole maker of the lithography machines needed to print them. That arrangement has held firm until now. A new American startup believes it has found a way to upend both. Its technology can reportedly print chips at the sub-nanometer scale in a single exposure, at roughly half the cost. And here's the part that most people overlook. This company has no interest in selling its machines. It wants to build entirely new chip factories around them. I've spent over a decade designing microchips. This industry is famously cautious. It advances in careful, incremental steps. What this startup is proposing is anything but incremental. If it works, it doesn't just threaten ASML and TSMC, it puts the entire model of advanced chip manufacturing at risk. Every major leap in microchip capability eventually collides with the same obstacle. How do you actually print the thing? Chip fabrication involves hundreds of tools and thousands of individual process steps, but one step sits above all the others. Lithography. An EUV lithography machine is arguably the most complex and expensive piece of manufacturing equipment ever built by humans. Its role sounds straightforward. It prints transistor features onto silicon wafers. In practice, it determines how small, how dense, and how powerful chips can become. At today's cutting edge, those features measure just a few nanometers across, more than 10,000 times thinner than a human hair. So how do you manufacture something that small with a machine the size of a bus? The answer is light. You shine light through a patterned mask onto a silicon wafer coated in light-sensitive chemistry. Where light lands, the chemistry reacts. Where it doesn't, material is selectively removed. Repeat this hundreds of times, layer after layer, and a chip gradually takes shape. And that's essentially how sand becomes a thinking machine. The concept is elegant. Making it work at nanometer scales is extraordinarily difficult. As transistors shrank, light itself became the limiting factor. Early lithography relied on deep ultraviolet light at a wavelength of 193 nanometers. It worked until physics wouldn't allow it to anymore. You simply can't reliably print features smaller than the wavelength of the light you're using. So the industry made a dramatic pivot. Extreme Ultraviolet Lithography, or EUV, uses light with a wavelength of just 13.5 nanometers, more than 10 times shorter than what came before. That single shift, combined with a cascade of hard-won engineering breakthroughs, is what unlocked today's most advanced chips. But EUV carries a steep price. EUV light is absorbed by nearly everything: air, glass, conventional lenses. The entire system must operate in near vacuum conditions. To generate EUV light, tiny droplets of molten tin are struck by high-powered lasers inside a vacuum chamber. And the resulting light is then guided using mirrors polished to near atomic precision. This technology took decades to develop, much of it originally pioneered in the United States. Today, only one company in the world can manufacture these machines, ASML, based in the Netherlands. Each unit costs roughly $400 million. Despite that price tag, the economics can work. A single EUV machine is capable of generating over $600 million worth of processed wafers per year. But the real challenge isn't purchasing the machine, it's mastering its operation. At the leading edge, only a handful of companies can do that reliably: TSMC, Samsung, and Intel. As transistor nodes shrink further, the printing challenge grows exponentially. At some point, you can no longer print the finest features in a single pass. The industry solution has been to split patterns across multiple exposures, a technique called multi-patterning. Think of it like drawing a series of fine lines with a marker that's too thick. You draw every other line on the first pass, then shift the template slightly and repeat. This allows you to produce patterns far denser than the tool could achieve in one shot. It works, but every additional pass means more masks, more process steps, and more opportunities for defects. Costs climb sharply. To push scaling further, ASML developed high-NA EUV, a more aggressive version of the same technology with more powerful optics. These machines are already operational at TSMC, Samsung, and Intel, but they come at an even greater cost, approaching $500 million per unit. The next planned step is Hyper-NA EUV, pushing the optics even harder to extract more resolution from the same light source. The machines grow larger, more complex, and more expensive with each generation. At some point, the machine becomes so costly that the chip it enables no longer makes financial sense. Leading-edge fabs are expected to cost $50 billion each by the end of this decade. Wafer prices are projected to approach $100,000 per wafer, and advanced chipmaking will increasingly be accessible only to companies with enormous capital reserves. Smaller players and new entrants will effectively be locked out. The pattern is clear. The industry keeps pushing the same fundamental technology even as costs rise faster than the benefits it delivers. Which raises a different question entirely. What if the problem isn't how far we can push EUV, but that we keep pushing EUV at all? This is where Substrate, a US-based startup, enters the picture. Rather than extending EUV further, Substrate is abandoning it completely and betting on X-ray lithography instead. The idea isn't new, researchers have explored it for decades, but execution has always been the sticking point. X-rays have far shorter wavelengths than anything used in modern fabs, but they're extremely difficult to manage. For a long time, the necessary optics simply didn't exist, and generating stable X-rays required synchrotrons, machines hundreds of meters long that occupied entire buildings, not exactly factory-friendly. Inside a synchrotron, electrons are accelerated to near the speed of light. Strong magnetic fields then bend their path, and that motion releases intense X-ray light. The concept is sound, the scale was the problem. What changed is not the underlying physics, but the supporting technology. Optics improved, X-ray sources became more compact, better control became possible. Substrate pulled these advances together and asked a simpler question. Instead of adding more masks and more complexity through multi-patterning, what if you just printed everything in a single exposure? If EUV lithography is like sketching a drawing, one line at a time, X-ray lithography aims to stamp the entire image in a single shot. X-rays used in this context operate in the range of a few angstroms, between 0.01 and 10 nanometers, which is up to 1,000 times shorter in wavelength than EUV. Shorter wavelengths mean smaller printable features, and in theory, that means better scaling potential. In practice, it's enormously difficult. X-rays pass through most materials rather than bending where you need them to, making precise control a persistent challenge. That's why this approach spent decades confined to academic papers. Substrate claims to have crossed enough of those barriers to make X-ray lithography a viable manufacturing tool. Substrate has been tight-lipped about the technical specifics of their system, understandably so, for competitive reasons, but they have published results. Their compact light source works by accelerating electrons to near relativistic speeds using radio frequency cavities. Those electrons then pass through precisely arranged magnetic structures that force them to oscillate. At these energy levels, that oscillation produces intense bursts of X-ray light. It's the same physical principle behind a synchrotron compressed down by orders of magnitude to fit within a factory tool. On the output side, Substrate has demonstrated printing of 12 nanometer features, directly relevant for building sub-2 nanometer transistors. They also claim single patterning across all layers, meaning they print in one pass what currently requires multiple complex steps. According to their data, the resolution they've achieved is comparable to ASML's most advanced high-NA EUV system. Feature size consistency across an entire wafer is reportedly accurate to within about 0.25 nanometers, a fraction of an atomic diameter. If these figures hold up under scrutiny, the implications are significant. More logic packed into a smaller area, printed in a single exposure using a tool that costs around $50 million rather than $500 million. At these advanced nodes, lithography alone isn't enough. X-rays don't interact with materials the same way EUV light does. They carry far more energy, which means the resists, masks, and optics that current fabs are built around simply won't function here. Substrate would need to reinvent the photoresist from scratch. The same applies to masks and optics. There's also the matter of X-ray damage. If not controlled precisely, X-rays can penetrate materials unintentionally, damaging transistors or introducing subtle defects that destroy manufacturing yield. And then there's throughput. Substrate currently has a working demonstration. Full-scale semiconductor manufacturing is an entirely different challenge. Making a process work once in a lab is one thing. Making it work reliably across hundreds of millions of wafers, day after day, year after year, that's the hard part. It's the reason most chip companies have exited leading-edge manufacturing altogether. For EUV, bridging that gap took over a decade. This is why Substrate isn't planning to sell tools. Instead, they intend to build their own factory in the United States, install and develop their own machines, work out the full manufacturing process, and then offer foundry services directly to customers. That puts them on a direct collision course with TSMC and Samsung. This isn't just about inventing a new piece of equipment. It's about inventing an entirely new factory and an entirely new foundry model. And by most estimates, it will take at least another 5 years. There's a reason NVIDIA remains fabless and leaves manufacturing entirely to TSMC. TSMC didn't simply purchase machines, they built manufacturing recipes over decades, investing hundreds of billions of dollars into yield, learning, process discipline, and operational scale. That investment only pays off because of volume. TSMC operates around 30 factories and produces roughly 1.6 million wafers every month, spread across numerous customers and product families. That combination of process mastery, scale, and packaging capability is what makes TSMC genuinely difficult to displace. It's worth noting that Substrate isn't alone in exploring particle accelerators as light sources. In the US, companies like Xlight and Inversion are also building accelerator-based light sources. Research programs are active in Europe, Japan, and China as well. But most of these efforts are solving a narrower problem: how to generate brighter EUV or soft X-ray light to push existing lithography further. Xlight, for example, is developing a free electron light source aimed at extending EUV, which fits within the existing industry roadmap and could eventually help ASML's tools go further, but wouldn't replace. To them, Substrate's ambition is categorically different. They're not trying to improve the current lithography step, they're trying to replace it entirely with a different tool and rebuild the entire chip manufacturing process around it. If Substrate's plan succeeds, the consequences extend well beyond semiconductor manufacturing. Advanced chipmaking is now deeply tied to economic power and national security. The most straightforward promise Substrate offers is this: costs drop significantly. To understand why that matters, consider what happened in space. For decades, space launch was a government-only domain. Launches were rare and breathtakingly expensive, tens of thousands of dollars per kilogram to orbit. Then SpaceX changed a single assumption: rockets don't have to be disposable. Reusability cut launch costs by roughly an order of magnitude. And that shift unlocked entirely new markets, faster development cycles, and industries that hadn't existed before. The same logic applies here. Cutting the cost of advanced chip manufacturing in half would have compounding effects for startups and smaller companies. Taping out at an advanced node currently costs millions of dollars, which means a single shot at getting it right Lower costs mean more attempts, faster iteration cycles, and ultimately more compute available for AI and the technologies built on top of it. Whether substrate ultimately succeeds remains genuinely uncertain. Chip manufacturing has humbled far larger and better resourced organizations, but the goal they're pursuing, a cheaper, faster, more accessible path to advanced chips, is exactly the kind of shift the industry needs.